So again, this is Roger Brewer with the Hawaii Department of Health. We're broadcasting from Honolulu. Also, Manny Nagaya, he's in Phoenix, I believe, at the moment. This is part 2 of a 2-part webinar on the use of TPH data for the risk-based evaluation of petroleum releases. So in part 1, we discussed some general TPH basics, TPH fallacies that we've all had if we've been doing this for kind of work for a long time, like I have over the past 20 years. So I like to quote Mark Twain: "It's not what we know that causes problems. It's not what we don't know that causes problems. It's what we know for sure that just ain't." So we've all dealt with these issues in the field. And we discussed potential environmental concerns associated with releases of petroleum and any contaminants in general, the chemistry and toxicity of TPH, and how we can use information about carbon ranges to develop TPH-based screening levels. We discussed a lot about TPH versus BTEX risk. So in part 2, first I want to give a quick review of part 1. Some people weren't able to join that segment of the webinar. And then we're going to go through the case studies in more detail. Also in part 1, we reviewed the former fuel tank farm case study. I'll give up a few notes on that, and then we'll get to the other 4. So in part 1, we discussed 3 references published by Hawaii Department of Health. One, the TPH Risk case studies document, latest update posted August 2018. We'll probably post another update next month, so we appreciate any comments and ideas and edits to that document. Second, to reference the risk-based TPH action levels, the screening levels published by our office, very similar to California's ESL's environmental screening levels, which I helped develop in the late 90s, early 2000s. Then some study we did on petroleum vapor intrusion, where we looked at the chemistry and toxicity of petroleum vapors for different fuels. And you see the web address there below, and there are links also to recorded webinars on the screening levels and our petroleum vapor intrusion guidance. We also discussed the ITRC risk document, and that document is going to go into a lot more detail about some of the topics we bring up today. A lot of the basics, background of TPH risk characterization, the chemistry of TPH degradation, products, conceptual site models, some notes about risk assessment and risk models, management of petroleum contaminated sites. They're not going to go into a lot of detail on the implementation of how to use TPH data to actually include in a risk assessment for contaminated sites. The document more provides the background. And also give a summary of the Hawaii Department of Health case studies. These case studies, as I mentioned, were originally intended to be an appendix to the ITRC document. But the document just became too long for ITRC to manage, so we opted to publish the case studies separately by DOH. It's referenced in the document. One thing about the ITRC TPH risk group I want to point out, it's kind of a once in a generation event, I think, getting 100 experts in petroleum together from regulators, consultants, oil industry. It's a pretty amazing group of people. And we were overwhelmed with the ideas to include in the case studies. We did the best we could to keep them succinct, but I'm sure there's a lot we could add. Also, kudos to the team leaders who managed this herd of cats, as we like to call ourselves, and actually got this document done. That was a major task. So the HDOH TPH risk case study document, the main report gives a quick review of risk-based approaches to TPH. And again, this has been going on for about 20 years. And I mentioned some references in part 1 dating back to the mid-1990s. So it's really nothing new. It's only been implemented fully by a few states so far. And also we talked about how the document discusses the use of existing TPH data, so you don't have to start over, common risk assessment problems, misconceptions, an overview of the case studies, and then details of the case studies in the attachments. And then the other attachments, 2 through 5, go into details about different technical topics associated with the case studies, from environmental concerns, development of screening levels, and even to mention a discussion of metabolite screening levels. So in part 1 also, we went over in a lot of detail potential environmental concerns posed by TPH, contaminated soil and groundwater. It's a lot more than just direct exposure. When you say risk assessment, traditionally, a lot of times we're only talking about direct exposure, maybe vapor intrusion these days, but there are a lot of other issues you have to consider, especially for petroleum, leaching and contamination of groundwater, impacts of dissolved phase plumes, degraded petroleum products, drinking water wells, gross contamination, which will one of my favorite topics we've had some good and bad experiences with. We'll discuss during the case studies. This can get pretty complicated. So it's really important from the beginning to ask the right questions for any type of contamination, especially petroleum. So the wrong question in this picture is, are there any sharks in this river? Well, no. But so the right question is it safe to swim in this river? So the first thing you have to do is start from the beginning and think about all the potential concerns about swimming in this river. And maybe it's more than just the animals in the river. And then you also have to think about what specific things you're going to look for. Should you be looking for sharks or alligators or snakes and other things? So it gets more complicated than a simplistic question. This is a lesson I learned one of my last consulting jobs. And as a risk assessor told me when I first started, risk assessments rarely lie, but they often don't tell the full truth. So the wrong question at this site, a former gas station site, is being redeveloped for, I think, a hotel or something, is there any benzene in the soil? That's all I was looking at the time. And then we got a call that the site was on fire. So the right question is, to start with, is it safe to dig in the soil? So you start from there. In this case, there wasn't any benzene or very minimal levels in the soil, but there were really high levels of TPH gasoline vapors in the soil caught on fire every time they drug a backhoe bucket through it. It's a big deal. It's definitely a potential concern for petroleum contaminated sites you have to think of. Very rare to happen. So it's more than just direct exposure and more than just benzene. So how do you address this problem? We started 20 years ago developing risk-based screening levels for TPH. And this is done, as we discussed, by splitting petroleum hydrocarbons up into 5 or 6 different carbon ranges, as we call them, aliphatics, aromatics. We assign physiochemical constants and toxicity factors to each one of these carbon ranges. And then we can develop screening levels or assess risk in the same manner that we calculate screening levels and assess risk for BTECs and pHs and other chemicals. Again, nothing new. It's a little bit complicated, but it can be done. So we can develop also carbon range weighted screening levels just for TPH gasoline or TPH diesel or heavy oil like we do for benzene and other chemicals. I like this approach. It makes it much more simple. So you see in this image, we've assigned screening levels. These are actually from Hawaii's guidance to each one of these specific environmental concerns. For soil, direct exposure, 450 ppm. If it's below that, it's in theory okay for your kid to play in the soil. Leaching contamination, TPH gasoline and groundwater, 700 ppm. If it's below that, you don't need to worry about this issue. But then look at gross contamination for soil, 100 ppm. So what does this mean? That's about the level you can start smelling petroleum contamination or gasoline in soil. This is equal to about 4 drops of gasoline in a double handful of soil. So you can try that at home. And so in this case, yeah, you probably wouldn't want soil with 450 ppm gasoline in it in your backyard or in your playground at 450 ppm. You'd definitely be able to smell that in the soil. Now, in theory, that doesn't pose a long-term health risk for kids playing in the soil, but you would definitely notice it. It's just going to cause some other problems. And if you dug into this soil, if it was buried deep, you're going to get a sudden emission of vapors that could pose short-term problems. And you can do the same thing for groundwater. Well, this all gets pretty complicated, lots and lots of numbers. I know I overwhelm people in the part 1 of the webinar with all these numbers and details. So in the end, and back to me and consulting in the field, it's going to make you really bug-eyed. So just give me a number. This was the intent of what we call the HDOH EAL surfer. California has something similar called the ESL surfer, Environmental Screening Level surfer. And this was originally developed by a good friend of mine, Laurent Millier, with the California EPA. When I was working for California EPA, we had like 70 tables of all these numbers, about 50,000 numbers. Laurent asked, he needed a project for an access database class at UC Berkeley. So I said, well, do this. Try this, Laurent. Make it easy. This is what he came up with. Now we use Excel. So just give me one number. Well, here's your one number for soil, TPH gasoline, 100 ppm. If you're below that, then you're done. If you're above that, there's different potential environmental concerns you need to think more about. They may or not be an issue at the site, but there's your one number. We can do the same thing for gasoline, TPHG, and drinking water, 300 ppb, indoor air, 290 micrograms per cubic meter. We can look at subslab soil vapor, 590 milligrams per cubic meter, and depending on your climate zone. So we can do the same thing for middle distillates, diesel, residual fuels. Here's your one number to start with. This is really helpful for site investigations just to get started. Parts from part 1, first ensure that all potential environmental concerns are considered at a site. And Also, risk-based screening levels can and have been developed for TPH carbon ranges and or carbon range weighted TPH. A big point we try to make, the TPH component of petroleum can still pose a risk even though concentrations of BTEX and such meet screening levels. This can cause a lot of angst for those of us who are only using BTEX in the past or even still now in closing sites. But some sites, especially things like diesel and such, we knew we still had a problem at the site because even though benzene levels were so low, but we weren't sure what to do. That's where the TPH screening levels come in handy. We'll discuss this more in some of the case studies. One thing we've noticed is BTEX-only assessments are probably okay for older releases of high benzene gasoline, where there was already lots of benzene in the soil. I'd still check. I'd still want TPH data myself, but we don't go back and look at old UST sites that were closed using only benzene data. In most cases, you dug up all the stinky stuff down to about 100 ppm, maybe left a small volume of stuff in place, but it's not going to pose long-term concerns. You just want to know where it is if someone digs into it in the future. Then again, consideration of TPH is especially important for newer releases, the low benzene gasoline. They started reducing levels of benzene and gasoline in 2005 and all types of middle distillates, diesel fuel and such. Okay, so as a quick overview of part one, so I'm going to give a quick summary of the case study for a former fuel terminal redevelopment project that we did. It's actually based on a project we did here in Hawaii. And like all these case studies, they're actually based on real life projects. Sometimes we combine projects, but even the data you see that we use in the case studies is, for the most part, is real. So in the former fuel tank terminal, so mostly gasoline where the tanks were, diesel fuel along the roadway here. And the site was going to be redeveloped for commercial use. In this case, it was actually a Lowe's store. Heavy contamination of gasoline under the tanks, heavy contamination of diesel along the roadway where these fuel pipelines were. In this case, we talked about using just bulk TPH data to initially investigate contaminated soil and contaminated groundwater and make calls on remediation that needed to be done there. For vapor intrusion, we actually, in this case study, we got carbon range data for soil vapors and then use that to develop site-specific screening levels for vapor intrusion. Here's some examples of how you can do this. This was the gasoline vapors. Again, this is real data. In this case, the gasoline, almost as it is always, was dominated by C5, C8 aliphatics, and just a little bit of other aromatics and aliphatics. So we have toxicity factors for each one of these carbon ranges. We can develop a weighted reference concentration or toxicity factor for gasoline vapors as a whole. Then we can develop indoor air screening levels, soil vapor screening levels, and such. For this particular example here, the ratio of TPH to benzene was 300 to 1. Once you get to 300 to 1 or lower, benzene's pretty much going to drive your vapor intrusion risk at a site. So if you only use benzene data, you're good to go as long as you use a stringent conservative risk, say 10 to the minus 6 risk. Diesel vapors, much higher proportion of C9, C8 plus aliphatics is more toxic than the lighter chain aliphatics. So your toxicity factor is lower, your indoor air and soil vapor screening levels are lower. And also, and this is real data again, I think from this site or across the street, but TPH to benzene ratio of 54,000 to 1. So there's no benzene in the soil vapors here. And you can meet screening levels for benzene for vapor intrusion and still have huge levels of TPH aliphatics that would obviously in the field pose vapor intrusion problems. So this is the case where you really have to look at TPH in addition to your indicator compounds. Then we use this data. This is what I like getting to, something you can hand the remediation people do with the risk assessment people. Here are the problems at the site. We call these environmental hazard maps. Here's where you have gross contamination concerns. Here's the area of contaminated soil and groundwater. You have vapor intrusion concerns and leaching and direct exposure and aquatic toxicity. And then they use this to develop a remediation plan and for long-term management. In this case study, and this is actually what happened at the site, we agreed just to dig up and treat the grossly contaminated soil, which gets rid of your really high-risk vapor problems and direct exposure problems, and get rid of the soil that poses vapor intrusion problems in general. And then you manage the rest in place. And we talked about lots of management options for the site, passive vapor barrier under the building, plugging sewer lines that lead to a nearby surface water body so that contaminated groundwater doesn't get in it and such. Some of the lessons there, lesson one, case study one, so you really need a well thought out CSM before you start an investigation. Get your risk assessors involved, get your remediation people involved. A direct comparison of total TPH data in soil in our experience is fine to do the job to address all concerns associated with contaminated soil and TPH. It's really useful to get carbon range data for soil vapor samples and develop site-specific screening levels. Well, you don't have to. We have default screening levels for TPH gasoline and TPH diesel vapors. They're probably too conservative for most sites. It's really useful to look at SGC silica gel cleanup data for groundwater, compare that to non-groundwater without silica gel cleanup data to make an assessment of the degradation status of petroleum in groundwater. That was case study 1, case study 2, a journal overview. Now let's get into the last 4 case studies. And again, these are based on real life experience and a lot of input from the ITRC team. So we give a lot of bulleted notes in the document, just something to think about. We could always go into a lot more detail. So case study number 2, gas stations, and by numbers, this is the most common type of petroleum contaminated site we deal with on a day-to-day basis by far. In this example, it was an active gas station. Petroleum type, we'll just say just gasoline, impacted media, soil vapor, groundwater. Highlighted topics for this case study, and we do this for all case studies. We try to highlight specific topics. So we talk about vapor intrusion. We talk about what we call in Hawaii single borehole DUs, where you're putting in single boreholes to identify the extent and relative magnitude of contamination, which we've always done at UST sites. We talk about de minimis contamination. Yeah, it's high concentration, but it's something, volume of soil, just a few cubic yards. Is it really an issue? We talk about all-site migration of dissolved phase plumes, and also metabolites or TPH-related degradation products in groundwater. The site setting, say it's an active gas station in use since the 1960s. Here's a catch we threw in as the gas station is adjacent to a school that has a shallow irrigation well that's used to water the lawns. Also inadvertently used by some of the workers and even students for drinking water. And this is kind of an actual case I worked on when I was working in California. Climate zone is cold. So we talked about this in the first webinar. This is used to assess vapor intrusion. Much higher risk of vapor intrusion concerns in cold climates where buildings are heated and less well ventilated they are in warmer climates or tropical climates. Depth to groundwater, 25 feet. We did this on purpose. Once you get more than about 15 feet to groundwater or even contaminated soil, then vapor intrusion problems associated with petroleum tend to be less significant just due to degradation. This is discussed in ITRC's PVI document. Primary COCPs, contaminants of potential concern, TPH gasoline, BTEX. Here's something really common too we put in. There are 2 releases at this site. First release before the year 2000, it was a small release discovered under dispensers during removal and upgrades of UST systems. And this is a release of high benzene gasoline, so some of this older gasoline that already had a lot of benzene in it. The majority of the contaminated soil was excavated and disposed of at a landfill, but as very common at active gas station sites, a small volume of soil, in this case less than 10 cubic yards, maybe your cubicle size or twice your cubicle, of impacted soil was left in place under a building due to structural concerns. Then we had a second release, a larger release from USTs discovered during routine leak detection monitoring of a new system. In this case, it was the newer low benzene gasoline, so much less than 5%. And in this case, L-NAPA was observed in groundwater monitoring wells. Remember, that's at 25 feet below ground surface. And all contamination is located under paved areas. There's no direct exposure in the sense that someone's being in contact with the soil, or even vapors being emitted from the soil to outdoor air. So site characterization, how do you characterize an active gasoline station site? People familiar with multi-increment sampling guidance, where it calls just from science and sampling theory, you need at least 30 borings just to characterize a single area. That's just not going to happen at a active gas station site. So what we do instead is what we've always done with some modifications, is you use single boreholes, and you collect soil samples from the boreholes and make observations to estimate the relative extent of contamination in the soil and a relative extent of contamination on groundwater. The catch here, though, is as you're taking the boring, you're going to collect a continuous core. And as you're collecting the core, you identify targeted layers within the core, maybe where you think it's contaminated or not contaminated, or you see staining. Then with each one of these intervals, we call these decision unit layers or decision unit intervals, you're going to collect a single sample, but not from a single random point within there. You're going to collect a sample across the entire interval. And since gasoline is a volatile chemical, You're going to collect at least 300 grams of soil from that interval, and you're going to put it in methanol in the field, send that to the laboratory, and they'll analyze it. And then you'll get a concentration of gasoline and BTEX for that targeted interval, much more representative than testing a random 5-gram discrete sample, randomly picked within that interval, which we've shown in the field. When you collect samples, discrete samples side by side, the concentration can vary by orders of magnitude. And this is something that it's not going to come out in the ITRC document, but if you go back and look at the 2012 ITRC ISM document, we discuss it in detail, and it's in a lot more detail in Hawaii's guidance. And unfortunately, in the ITRC TPH Risk document, the people who are writing the section on site investigation weren't familiar with these incremental sampling methodologies, they call it, their techniques. And there may be some notes in there about collecting discrete samples in the subsurface. But those, from our experience, these aren't going to be reliable. We would definitely recommend using ISM type samples. So we collected our soil, groundwater, and soil vapor samples at the site. This is a gas station, probably a lower budget investigation. We're not going to deal with carbon range data. We're just going to use the bulk TPH data for soil, groundwater, and soil vapor to assess potential environmental concerns. The potential environmental concerns for the first release, actually this notice is incorrect. Note on the slide, it should say high benzene gasoline. I'll fix that when I post the final slides to our web page. So soil sample data for 10 cubic yards of soil left on the building exceeds screening levels for all potential environmental concerns. Not a big surprise. Also, soil vapor samples collected on the building exceed vapor intrusion screening levels for TPH gasoline and benzene. So in this case, the ratio of benzene, TPH to benzene, was 30-1 in the vapor zone of this building. That's a lot of benzene. Remember, we said under 300-1 benzene is probably going to drive risk. So in this case, benzene, it would drive theoretical vapor intrusion risk to the overlying building. The issue here is that just means TPH and vapors are unlikely to exceed vapor intrusion screening levels once you meet benzene levels. However, if you look at the mass balance issues with this, there's insufficient volume of contamination to pose long-term vapor intrusion concerns at this site. It's only 10 cubic yards of soil, only a few cups of gasoline or a gallon of gasoline or something left. So we would refer this as de minimis contamination in our office and just manage the soil in place. And you can see some example screening levels and data for benzene and gasoline at the site. The second release, which in this case was low benzene gasoline. So in this case, the soil and groundwater data indicates significant gasoline contamination under one of the USTs. There's LNAPL on the groundwater, but it doesn't extend off-site. There's a strong potential, though, for an off-site extent of a dissolved phase plume. This hasn't been determined yet. Subslab soil vapor samples under the main building tested for TPH. Here I said carbon ranges. Actually, we just use bulk TPH, and for BTEX. And soil vapor samples exceeded vapor intrusion screening levels for carbon range weighted TPH and benzene, which we use to assess the site. And in this case, TPH drives vapor intrusion risk over benzene. The ratio of TPH to benzene was over 1,000-1 for this low benzene gasoline. So in this case, you could meet benzene screening levels of vapor intrusion, but still have a serious potential serious TPH vapor intrusion problem. So TPH is still likely to exceed vapor intrusion screening levels, even though benzene screening levels are met. Again, this is real data that we collected from sites where benzene and soil vapor is 43 milligrams per cubic meter, gasoline 130,000 milligrams per cubic meter. So in this case, TPH gasoline is the risk driver in the problem. Potential environmental concerns at this site is direct exposure to construction workers. There's really no direct exposure now because the whole site's paved. Some vapor intrusion issues, especially for the main building over the low benzene gasoline release. Potential leaching of gasoline from soil, if they had landscaped areas that are irrigated, and exacerbation of groundwater contamination. Gross contamination concerns under both buildings and around the tank. So if someone digs into this in the future to do some type of utility work, need to be aware you could get short-term but very strong emissions of high gasoline vapors that could pose short-term risk problems for workers and people around there. And then the fifth one was impacts to the irrigation well, inadvertent use for drinking water. The groundwater data, where you compare silica gel, non-silica gel data, indicate that groundwater, not surprisingly, is dominated by TPH-related metabolites outside of the LNAPL area. One thing at gasoline sites, you always want to test for TPH gasoline and TPH diesel range compounds in the groundwater. And it's these metabolites or the breakdown products that start showing up in diesel range because they're not volatile anymore. Even though there's no diesel there, that's where your degradation products show up. So you always want to test for diesel, even at a gasoline release site. So you can also, at this site, we have potential impacts on this off-site irrigation well. We're concerned about TPH-related metabolites in drinking water. We don't go into a lot of detail of this in the case study, but there's an attachment 5 where we discuss the calculation of risk-based screening levels for TPH-related metabolites. This is based on some work by Don Zemo and others in 2016 and other papers. It's still under design, but what they did is they designated metabolite families to degradation products and then assigned toxicity factors to each one of these families. So from initial degradation to older degradation, you have alcohols, esters, acids, ketones, aldehydes, phenols. These are all the metabolite families. Since we have toxicity factors for it, we can estimate metabolite family makeup of different degradation stages or degraded TPH. Now we can calculate metabolite weighted toxicity factors for these different states of degraded gasoline, or in this case they were looking at diesel and groundwater. And we can calculate metabolite sweet weighted screening levels in the same way we do for TPH or benzene. It's just an example of different degradation suites that they proposed in their paper in the makeup of each one of these different stages of degradation of petroleum and groundwater. So I won't go through this in detail, but basically blue is bad, green is good. So you can see from stage 1, there's lots of blue that's more toxic, to stage 4 where there's lots of green, so it's less toxic. This is, if you take their data and their metabolite suites for each degradation stage where they look at their lowest, most conservative toxicity factors, you can actually develop screening levels for TPH-related metabolites in drinking water and groundwater. So in this case, using their data, you come up with a screening level of 420 micrograms per liter TPH-related metabolites right under the LNAPL, which is really interesting because they were looking at diesel again. So our purely diesel-based number for dissolved diesel TPH in groundwater or drinking water is 400 micrograms per liter. So they basically concurred with what we see for TPH diesel in general before it's degraded. They also suggest in their study that as the compounds in groundwater get more and more degraded, maybe as you move away from the source area, the metabolite suites and the combined become less and less toxic. So you move from 420 micrograms per liter as your risk-based screening level for drinking water to 1,400 micrograms per liter in stage 4, where you're well away from the LNAPL source area and the hydrocarbons are highly degraded. So the accuracy of these TPH toxicity factors in this whole approach is still being strongly developed, but I think for me it was one of the most useful things to come out of the ITRC TPH risk group. This is, I think, where we're going in the future. Now it doesn't really matter as you get out to stage 4, 1,400 micrograms per liter TPH-related metabolites. That water is probably going to smell pretty bad and taste really bad. So even though it's not toxic in theory, no one's still going to drink it. That's the nice thing with petroleum. In most cases, you're going to be well aware that you're being exposed either through smelling it or tasting it before you hit a level that really poses high risk. Site remediation monitoring, the remedial actions here, they seal the cracks and utility gaps in the floors of all the buildings, even the one with a small pocket of gasoline contaminated soil under the floor could pose short-term vapor problems. Consider soil vapor extraction to reduce the mass of gasoline beneath the slab and replenish oxygen. Consider removal of free product on the groundwater. Again, once you clean up under the tanks and such, the free product on groundwater is mainly a problem for continued groundwater contamination, probably not vapor intrusion. It's just too deep. I'd still check. Install additional monitoring wells to see what's going on at the irrigation well, and then monitor the irrigation well for TPH or total organic carbon with and without silica gel cleanup and BTEX. Then mainly prepare an environmental hazard management plan. Map where this contamination is, and so that in the future, when the initial crew is gone, future people know what's underground before they start digging into it. Some of the lessons learned, total TPH data for gasoline vapors is usually useful for initial screening, although site-specific carbon range data can be useful. So TPH and soil vapors can still pose significant vapor intrusion risk if the LNAPL is very close to contaminated soil close to a building for low benzene gasoline releases, even though benzene vapors may not be an issue. Again, probably not an issue for older sites because most of the stinky dirt was dug up and is high benzene gasoline. So if you're just using BTEX back then, you're probably okay. The overall toxicity of TPH-related degradation compounds is probably similar to the parent hydrocarbons when you're close to the El-naphtha source. They could be less toxic as you move away from the El-naphtha source. That's still being debated and discussed. And in the end, the water is probably going to taste bad, smell bad by the time you get to 500 or 1,000 micrograms per cubic liter anyway. So that was the gas station site. Next, look at the tanker spill. This is a little shorter. It's actually, again, based on a real-life tanker spill. I think it was in Pennsylvania that someone in the group discussed with us. This now current status, long-term monitoring. It was a diesel tanker truck. Impacted soil, air, surface water, and sediment. Highlighted topics: emergency response, short-term risk, MIS, ISM sampling again, soil sampling, stream impact, silica gel cleanup, which we always include. Site setting: release of 3,000 gallons from a diesel truck, tanker truck that flipped over in a densely populated residential neighborhood. I think we have it in front of an apartment complex. We threw this in. The truck clipped a telephone pole as it was crashing in a non-PCB transformer filled with low toxicity mineral oil, fell down and broke open in a yard. So you have to deal with that also. Primary CFPCs, TPH diesel, BTEX, naphthalene, and mineral oil. Some of the fuel flowed into the front yard of an apartment building. Contamination is limited to the upper 3 to 5 feet. There's no concerns about groundwater about 40 feet deep. The remaining fuel went into a storm drain and then went into a small stream. Potential environmental concerns then are direct exposure to especially short-term vapor emissions for the residents and people, workers trying to address the spill. Second was runoff in the storm sewer into the stream, impacts to aquatic habitats. And then third, again, just gross contamination, which I guess this would be more related to short-term vapor emissions. With direct exposure is more long-term vapor emissions if you don't do anything at the site. Initial response action, but said TPH aliphatics, especially for diesel fuel, we know up front are going to be the primary short-term exposure concern for vapors being emitted. We did a big study of diesel vapor chemistry and toxicity and published it in 2013. So there might be some dizzy and nausea caused by short-term exposure to vapors, but this is all transitory, reversible. It's not going to cause any long-term health problems, and it's quickly dissipated once you leave the area, once the area is cleaned up. So residents in the adjacent building temporarily evacuated. On-site mobile lab is set up because this is a site where you need to get in and get out. You don't have time to do a detailed risk assessment and testing soil, air, water samples. I think with sediment too. So environmentally friendly foam suppressants quickly used to reduce vapor emissions and fire concerns. Screening levels used, again, we're getting in and getting out with this site. We know what it is. We know what its diesel fuel, the general makeup. So we just use bulk TPH data for soil, air, and surface water to make initial cleanup and remediation decisions. Some of the air monitoring data we threw in, again, this is from actual data, but to evaluate short-term risks, this was something I wasn't aware of. Someone pointed out in the ITRC group. The emergency response planning guidance says short-term risk levels for TPH vapors, 300,000 micrograms per cubic meter. So if it's less than this concentration, there may be some nuisance concerns, but we don't expect any long-term health impacts. You see the same level for benzene. Long-term risk screening level, this is our ambient air number for TPH and benzene, much lower than that, of course. Odor threshold, you can start to smell diesel vapors at around 5,000 micrograms per cubic meter. Benzene, not that smelly, about 5,000 also, whereas naphthalene, much lower odor threshold. That's what makes diesel and other fuels stink. Although actually in diesel, it's mostly the aliphatics. So you see the data for the release upwind and in the release area, upwind and downwind. In the release area, no big surprises. You can definitely smell it well above the odor threshold. Not necessarily above short-term risk, so it's okay for the workers to get in and do their work without respiratory protection, although they may opt to do that anyway. Again, the main short-term vapor risk is from the TPH, not necessarily the benzene. The benzene is well below any levels for short-term risk. For remediation actions, then they dug up the soil where it had flowed into the grassy areas in front of the apartment building. In this case, though, we don't collect discrete samples anymore. We know if you move a sample over 2 feet or 2 inches, you can get a completely different number. So we don't go into a lot of detail. We designated 8 or 10 different decision units, as we call it, or targeted areas to collect a single sample. In each one of these areas, we collected a 1 to 2 kilogram sample from 30 or 40 or 50 points, combined it together, and sent that to the lab for testing. So we get much more representative data much more reliable data for cleaning up a site. In one of the areas, most heavily contaminated areas, we collected 3 completely independent samples just to verify that our samples represented those areas. Then the data were compared to a Tier 1 residential screening level for TPH diesel, which in this case is the lowest screening level is direct exposure. That gave me one number, 220 ppm. That's going to take care of all your potential problems, gross contamination and leaching concern. And in the case study, they took out a few more feet of soil from one of the decision unit areas. Now this transformer spill area, transformer oil is not toxic. The main concern again is gross contamination. It may be a little stinky and waxy feeling. So you dig up the stinky and waxy feeling dirt and you're done. It's about 5,000 ppm. But it'll relieve any concerns in the future about, hey, what's this in the soil? Stream remedial actions, booms and sorbent pads used to control LNAPL, heavily contaminated contamination removed from easily accessible areas. Then it was just the sheens were allowed to naturally attenuate over time due to evaporation, aerobic biodegradation, photooxidation, dissolution. This is really fun to include in these case studies. We got a lot of good information on fate and transport of petroleum from the ITRC group. Additional removal or treatment of contaminated sediment and soil was deemed to pose a higher risk to the stream ecology than just letting it to naturally attenuate. And water samples collected a few months later, no big surprise, indicated no hydrocarbons left and minimal polar compounds, probably background. Lessons learned here. Rapid assessment of fuel characteristics, migration pathways, soil properties, etc. is necessary for initial response action and to prioritize what you can do at the site. So again, you have to get in and get out. Initial health concerns posed by TPH, aliphatics, again, this is diesel fuel. Even naphthalene levels, if you look at soil vapor data, it's the aliphatics is what you're smelling, what poses the main concern. Short-term but transitory health effects. So once you clean it up and get people out of the area, it's not a big problem. And monitoring and cleanup expedited by use of published comprehensive carbon range weighted screening levels for TPH. So they cover all potential environmental concerns. You don't have to worry once you get in and get out that you may not have addressed some issue. And then natural degradations was adequate to address remaining impacts to the stream following removal of free product and heavily contaminated vegetation sediment. That was case study number 3. And case study number 4. This was my favorite case study, I have to say, a pipeline release. It was crude oil in a remote area, which we'll go into in detail. Impacted media, soil, sediment, and surface water, highlighted topics. Impacts to aquatic toxicity, really interesting, especially petroleum fate and transport. We had some great people in the ITR Risk group that had been looking at a site very similar to what I'm talking about for 30 years. So they really had the fate and transport and long-term degradation of such of light crude oil down. We tried to incorporate that into the case study. We talk a lot about the geochemistry of degrading petroleum products. They also use non-volatile dissolved organic carbon test, or really total organic carbon, but it's not volatile, to monitor the groundwater plume. That's kind of tricky because there's already naturally high organic carbon in the groundwater, so you have to have a good idea of background, but it's very useful and something I think our office will look to in the future for trying to map out petroleum plumes in groundwater, just because the standard TPH test for hydrocarbons for groundwater aren't really reliable. Here's a picture of a pipeline release if you haven't ever seen these. So I used to do some work around oil and gas fields in South America, and we saw quite a few sites that actually did look like this, and they're a big mess and very difficult to deal with. Release scenario, it's a ruptured pipeline release of 250,000 gallons of light crude oil into the wetland. There's no public access. It's a remote area, several miles from the nearest population center, rapidly spread out, disseminated throughout the marsh. A lot of strong vapors, obviously you'd be able to smell this stuff. And immediate acute effects on plants, fish, reptiles, benthic organisms, birds, and such in the immediate release area just due to LNAPL and oxygen depletion. Initial response action, temporary access roads constructed, booms and sorbent pads were used to recover LNAPL, minimize further spread throughout the marsh and in the marsh into streams and such. In this case, it's crude oil, so we're not going to initially rely on the default screening levels and makeup of gasoline and diesel. We want to get carbon range data for this contamination. Also standard BTEX and pH data obtained for the samples to release crude oil. So we know what was released. Again, air monitoring initially confirmed vapors dominated by C5, C12 aliphatics, not a big surprise, with minor components of aromatics. So again, aliphatics in this case drive short-term inhalation risk for workers, not your individual aromatics. So it's easily accessible, heavily contaminated soil, sediment, vegetation is removed. The approximate lateral extent of soil, sediment, water contamination is estimated from drone photographs. This is going to be a drawn-out event, so a detailed investigation and assessment of the impacts was planned, but everyone knew it was going to take a while after the initial actions. Here's a crude oil carbon range chemistry. This is actual data that was published for fresh West Texas intermediate light crude oil. A little bit of C5, C8 aliphatics, mostly dominated by your middle range C9, C18 plus aliphatic compounds, and a little bit of heavier aromatics. So it looks kind of like diesel fuel, but thicker. Again, the lighter range aliphatics are the most volatile, so it's not a big surprise that the vapors are dominated by these. Here's a petroleum fate and transport scenario that's in this case study. So we gave a lot of references on this. It's really fun and interesting to put together. So first you had overland flow of the petroleum into the marsh, and initial degradation by off-gassing, aerobic biodegradation, photo-oxidation. And then as it moved into the marsh area, dissolution of hydrocarbons, and it's already starting to degrade metabolites into the surface water. You also had dissolution of the petroleum into the groundwater, which is only a few feet below the pipeline in this scenario. And here your initial aerobic degradation, pretty quickly it goes anaerobic, and you have this dissolved phase plume of degraded hydrocarbons migrating and discharging into the marsh area. Status 3 months later. So the surface water sheen is mostly dissipated from the marsh, except localized areas along the edge of the marsh where they couldn't really get to the El Napo. Evaporation volatilization were the initial primary attenuation mechanisms. This caused a progressive enrichment of the residual petroleum and higher weight, more viscous compounds, so it's starting to get thicker and gooier. But now after 3 months, biodegradation is becoming more dominant. And this was really interesting as emulsification and deposition of sedimentation of tar balls is starting to occur within the marsh. So the oil, El Napo, is floating on the surface of the marsh. As the petroleum degrades, it becomes more viscous and also more dense. So you start to get these small tar balls kind of raining down from the El Napo into the marsh sediments. That's going to pose a problem for sediment sampling we'll talk about in a minute. Then a detailed soil, groundwater, surface water, and sediment investigation were carried out. In this case, the screening levels used, again, for soil, because it was crude oil, we're getting carbon range data to get a better idea of what exactly was left in the soil, especially for leaching and gross contamination concerns, to identify where your main contamination is. We're not so worried about direct exposure, vapor intrusion. We could be worried about terrestrial ecotoxicity also. I don't think we went in that in too much detail. It's more site-specific call. Sediment also getting carbon range data to look at benthic toxicity. In the groundwater and surface water, though, or sediment pore water, we're looking at total TPH data, or in this case, using total non-volatile organic carbon compounds. This TNVOC data was total organic carbon, to try to get an idea of where the degraded hydrocarbons are in the groundwater and in the surface water. Again, this side also we did a big multi-increment sampling or incremental sampling methodology sediment sample collection, which we've been doing this in Hawaii for 10 years. It's been starting on the mainland the last 5 years. Designated 8 different areas of the marsh where we see more heavy contamination to go out and collect sediment samples and surface water samples. Each of these 8 areas, we collected a sediment sample right along the shoreline, and then off in the deeper water, we collected a second sediment sample. So we had 16 total decision units, as we call them. Instead of just grabbing a random handful of sediment and putting it in a 4-ounce jar and sent to the lab, in each one of these decision unit areas, we collected, we can say the upper 6 inches or whatever target depth cores. We went through and collected 30 to 50 cores from each targeted area, combined that into a single sample. And there's a lot of statistics and reasons behind, in science theory, behind 30 to 50 points. And you collect a minimum 1 to 2 kilograms of sediment to get a representative sample. This is all combined, and then that was submitted to the laboratory for testing. When they get it, they don't just open the bag or whatever you put it in and grab a random 10-gram spoonful and test it. They have to spread it out. And since this stuff is semi-volatile, they collect another, I'd say 10-gram or 30-gram aliquot from 30 to 50 points within that sample and test it. So now the data that the laboratory gives you is representative of the sample. The sample is representative of where you took it in the field. Characterization results, so there's still isolated visible pockets of degraded petroleum really can't get to very well in the vegetation and some sheens in those areas. Dissolved phase TPH and TPH-related metabolites not detected at this point several months later in the surface water samples away from these other areas. Sediment sample carbon range data in some areas exceeded screening levels for toxicity to benthic organisms. We still had some heavy contamination. The total TPH data for sediment pore water exceeded screening levels for aquatic toxicity. The SGC data that confirmed that near total degradation of these hydrocarbons in the pore water to polar metabolites. And the metabolites, though, are at this stage are still assumed to have a similar toxicity to the parent hydrocarbons, pending site-specific studies. Here's just an example of some of the sediment data for the site. Massachusetts actually published aquatic toxicity or benthic toxicity screening levels for individual carbon ranges. So you see those highlighted here in the first carbon. So in the sediment data, we showed there's a lot of contamination still left in a few of the shoreline areas where the mean concentration of the samples collected in these DUs is much higher than the screening levels. In each one of these DUs, we actually collected 3 separate samples, 3 independent samples, and compared the results just to see if we were getting reproducible data. They all exceed the screening levels, but look at the relative standard deviations here. And look at the ISM document, ITRC published, or our document that talks about this. Once you get a relative standard deviation of 35%, you can't really rely on that data, or the samples aren't necessarily reproducible. So in this case, the data, we go back to the same area and collect 3 separate samples and get 3 separate numbers. And why is that happening? It's because there's a lot of these little tiny tar balls in the sediment. And when that happens, you have to collect a really big sample from lots and lots of points to get a representative sample. It's an example of pore water, groundwater data for the site. The sediment pore water along the shoreline, maximum concentration without silica gel cleanup, 3,200 micrograms per liter. With silica gel cleanup, only 200, so it's mostly degraded compounds. We compare that to an aquatic toxicity screening level. This is published in California back in the 90s. We still use 640 micrograms per liter. So it's still a problem in the heavily contaminated areas, the pore water and the sediments for benthic organisms. Groundwater, much higher, maximum concentration, 17,000 micrograms per liter. And with silica gel cleanup, it notes that most of that is degraded hydrocarbon compounds. This throws up a flag. Why is the concentration of this crude oil or diesel range stuff in groundwater higher than the solubility level, which for this typically be less than 5,000 micrograms per liter? That's because it's mostly degraded compounds, these metabolites that have a higher solubility than the original diesel fuel. Also noted here was that your standard TPH diesel tests for these water samples compared to the total organic carbon test suggested that you're missing about 30% of the petroleum-related parent compounds and metabolites in the groundwater using just TPHD. That's why they suggest that the total non-volatile organic carbon data are there. Additional remedial actions here. Continued periodic removal of sheens and free product that appear along the marsh edges. You can access them. Quarterly monitoring. Again, use of this dissolved organic carbon data to monitor the groundwater, get a better idea of where the plume is. Use of groundwater samples now to develop more site-specific acute and chronic sediment and aquatic toxicity screening levels for these degraded compounds instead of the default values published. And then you could do some potential targeted treatment of impacted groundwater and even sediment that exceeds the acute toxicity levels and carry out additional remediation as needed and is accessible to the point where you're not causing more damage than you're helping. Some of the lessons learned: emergency response to spills in remote areas. A place like this, your main concern is going to be aquatic and benthic community impacts. So another set of concerns you have to think about and bring in eco-risk assessors up front. So your conceptual site model needs to consider both short and long-term impacts to receptors. You also have to consider sort of complex degradation and migration pathways of petroleum, in this case into wetlands and sensitive populations. So the hydrocarbons may be gone, but the breakdown products still could cause problems. And also consider use of, again, of this non-volatile dissolved organic carbon data to assess and monitor, identify the contamination of surface water and groundwater instead of standard TPH. Something we haven't done yet, but we're definitely looking into. Okay, last case study, and this is pretty short, but also very interesting. It's from our colleague in Texas. We added oil and gas field. This case is now under long-term management. The main type of contamination was drilling fluid, a petroleum-based drilling fluid used to drill the oil and gas wells. Impacted media, soil, and groundwater. Highlighted topics: the Texas method 1005 for TPH, which we may switch to in Hawaii pretty soon. I think it's much more useful for TPH than your standard TPHG, TPHD type methods. Also, something really interesting here that, again, I want to look to in more detail: laboratory leaching tests for leaching of petroleum and other contaminants out of soil. These leach methods are called. Something else we need to look at in more detail, and long-term management of sites. Site setting: oil and gas exploration production site with 3,000 acres, very remote, active cattle ranch, about 10 miles from the nearest community, half mile from the nearest surface water body. It's a freshwater well located on the ranch, and not too far from where the contamination is, used for irrigation and for cattle, drinking water for cattle. Groundwater is only about 15 feet. Well cuttings coated with drilling fluids. This is diesel plus organic additives and crude oil. In this case, were placed in a poorly constructed and maintained clay line pits. So basically, the people that drilled the well made a mess. They're supposed to put all this stuff in a pit, cap it well, and manage it on site, but they didn't do a very good job. Landowner discovered blackened oily vegetable nail apple in the surface area around the well and all the way to the waste pit several months after completion of the oil and gas well. Site characterization: the primary CFPCs, TPH diesel, TPH O for the crude oil, although there wasn't really much there. It's mostly the drilling fluid. And BTEX, heavy metals, salinity. They probably also test for pHs. Salinity is a really big issue for oil and gas wells. You get a lot of brine when you drill a well, and this stuff, it's not that toxic in terms of your typical contaminants, but the salinity can be so high that it's highly toxic to plant life. And that's something you have to take into consideration with soil that's contaminated by brines, or in Hawaii, in that case, it's soil or sediment dredged from harbors and other marine areas that has a very high salinity and it's very toxic to plant life used up in the areas. Representative ISM samples, again, collected of soil and drill cuttings, samples of groundwater, the monitoring wells collected. Samples were analyzed for TPH using the Texas Commission for Environmental Quality, again, method 1005 plus BTEX chlorides for that salinity. They probably looked at a few other things, and heavy metals. Again, TPH in this case dominated by C6, C28 aliphatics, mostly diesel range. Soil and groundwater samples exceeded TPH screening levels for TPH, but not for BTEX, pHs, heavy metals were pretty negligible in this case. So SGC data for groundwater indicated, not surprisingly, that the contamination was dominated by TPH-related polar metabolites. Your parent hydrocarbons are mostly gone. Environmental concerns. First is human exposure to just workers around this site. Also exposure to cattle. They're walking across heavy contamination, and also plant uptake, or at least petroleum on the plants that the cattle could be eating. Probably the petroleum, in my experience, would kill the plant before it actually gets taken up to a level that would cause harm to cattle or other wildlife. And then there's the contaminated groundwater that's used to feed the cattle trough well used for drinking water there for the cattle. Leaching of oil was a big issue from the waste pit that wasn't really very well designed. Continued impacts to groundwater. And then just general gross contamination. There's still a lot of vapors and stuff coming off. This heavy contamination around the site. And when it rains, you're getting sheens and stuff coming off the waste pit where the elm apples are and going into the stream. This was a really interesting addition to this case study, the remedial objectives. And again, this is all based on a real case that our colleague from Texas and ITRC group wrote up for this case study. So the main goal was to minimize TPH risk to humans and cattle, including impacts to vegetation. Also minimize TPH migration to groundwater and surface water. And so in this case, they developed a site-specific surface soil TPH screening level, 220 ppm, not really site-specific. It's like the default we use here in Hawaii. But that was applied to the site. Also, a site-specific groundwater TPH screening level of 1 milligram per liter was implemented in the absence of silica gel cleanup. This was at the wellhead where they're using it to pump into the trough primarily for cattle use. They assumed that was adequate. They used this to develop a site-specific soil leachate screening level for TPH of 100 milligrams per liter within the waste oil pit, the waste pit. This was developed based on estimated attenuation before it ever reached the well, which is located a short distance away. And then a site-specific waste pit soil TPH cleanup level of 10,000 milligrams per kilogram was developed based on the results of solidification and stabilization tests and leaching tests run on the soil. So any soil with less than 10,000 ppm TPH wasn't going to generate a leachate with greater than more than 100 milligrams per liter TPH in it. And this was going to be adequate to protect the well, nearby well, you ensured TPH wouldn't be over 1 ppm, 1 milligram per liter in that water that was being used to give to the cattle. Medial action, all the free phase, LNAPA removed from the waste pit with a vacuum truck. Soil with greater than 10,000 ppm TPH diesel excavated and disposed of. Soil with greater than 220 milligrams per kilogram TPH and less than 10,000 ppm excavated and consolidated within a newly designed and better aligned burial pit. In situ solidification and stabilization was carried out for 1,800 cubic yards of soil and drill cuttings placed in the pit. There's some references, including the case study, on how this was done. I actually don't have much experience in this. And then long-term environmental hazard management plan was prepared. No additional engineering or institutional controls, just document where this stuff is and how to manage it. Lessons learned, consider the use of both TPH and indicator compounds such as BTEX for crude oil releases. And also organic additives that added to petroleum fuels, in this case, can significantly affect the mobility, increase the solubility of these fuels. Even though they're using diesel fuel in the drill cutting for drilling, solubility is much higher than typical diesel fuel because of all the additives. This is something you have to think about and have a much more thorough understanding of drilling fluids beyond your standard MSDS sheets, or in a site-specific case. Biodegradation M&A weren't alone adequate to address contamination at this site. This was interesting because of the additives in the drilling fluid, which were intentionally used to inhibit biological action during drilling and impacts your oil resources at depth. And they used laboratory-based leaching tests, which is really another direction we need to head to develop site-specific soil screening levels, protection of groundwater. So that's it. 5 different case studies. We still have some time for questions. Also, these webinars are being recorded. They'll be posted to our YouTube state webpage or YouTube channel. I'll fix any last edits to the slides and post those to our webpage in the next few days. We should have the YouTube publications or recordings posted to our webpage sometime next week. So at this point, I'd be happy to take any questions, comments, ideas. We'd like to keep these case studies green. So any ideas for additions to them or additional case studies, let us know, and Manny and I can work with others to add them to this document and help consolidate a lot of the ideas we've been working on for a long time.
Thanks,
so, Vicki,
Roger. It's Vicki. I do have a couple of questions in the chat box. The first one is from Angela. It says, when should we use the silica gel cleanup?
So I like silica gel cleanup. I would always use it at a site where you have contaminated groundwater, just so you can document that contaminant, that degradation is taking place, if nothing else. And show me one site where it's not taking place. I've never seen a site where it isn't, but it's important to have both types of data. The issue is that for initial comparison to screening levels, we pretty much have to assume at this point that the hydrocarbon degradation products have the same toxicity as the parent compounds. So you want to compare the non-silica gel data to your screening levels initially. But I always get both. It's good to document degradation and that Mother Nature is taking care of things at a site probably better than you can do by injecting stuff into the groundwater or other types of treatment.
Okay, the second question is from Hal. It's, what TPH metabolites are healthy for us to ingest?
Well, that, at low concentrations and low doses, none of these metabolites pose a health risk. Same thing for diesel fuel. I think I actually wrote it down somewhere, like 1 drop of diesel fuel, if you drink that per month, isn't going to pose any significant health issues or health risk. So just keep in mind that dose makes the poison. Anything is toxic above a certain dose. Water is toxic. If you drink more than 5 gallons, 3 to 5 gallons of water at one time, then it'll probably kill you, just because, I forget the specific term, but it causes your cells in your body to explode. Your oxygen is toxic above a concentration. So you have to keep that in mind. And with the metabolites, there's still a lot of debates and discussions going on about what the exact toxicity is. And that's something that I'm sure several people are already working on over the next few years.
Hal also had a statement, I guess, in regards to that question. It said, reliance on taste and odor thresholds to protect against exposure neglects to consider that some, many, or most exposure scenarios start out with low concentrations that cannot be smelled or tasted. Over time, those exposed become desensitized. By the time the problem is recognized, people have been exposed for long periods of time at increasing concentrations.
Yeah, that's an important point. This is why you can't just go by the smell or the taste of contamination for petroleum or anything at the site. You have to collect good data, good representative data for the site, and then compare that to risk-based screening levels or do a risk assessment. So you can't completely rely on your natural senses to identify when you're in a situation that could pose health risk.
Any more questions? The last was a question about if the recording of the Monday part 1 is available. So I posted the link. Roger, are we going to send out a link when they are both posted?
Yeah, so I posted the slides. I don't think I have any more edits to part 1 slides. I definitely do for part 2. So I'll repost the slides in the next day or two and the recordings, and we'll send a note out next week when the recordings are uploaded to YouTube.
Well, that's all the questions that were posted in the chat.
Okay. So if there are no more questions, then be glad to take any questions. You have Manny's email address at the front slide here. So any questions, comments, ideas on these case studies are welcome, and it'd be something fun to work on again for the next few years. We've learned a lot in the last 20 years. I'm sure we still have a lot to learn. So thanks everyone for joining in, and we'll keep in touch.